Hello, welcome ECE 492. I believe in previous 7 videos, we gave a very general introduction of the model building through the least mean square method. And it's really very condensed 7 videos, including a lot of concept and a lot of equations in that 7 videos. It's sometimes really hard to understand all this concept. And therefore, I'd like to connect the problem we are going to solve with all this concept. Therefore, it can give us some better feeling about this knowledge and all these equations. And this is the problem we are going to solve for the first computer experiment. So here we have 2 groups of stars, the red stars and the blue stars. The red stars on the top left corner and the blue stars on the bottom right corners. So we can see basically all these groups stars, they group together, of course. And if we know their coordinate, we can tell these stars belong to which group. So on this left top corner, normally the x1 is negative value, maybe sometimes positive value, but the x2 normally is really positive value, above -5 and even higher value. For the blue stars, they are on the bottom right corner. So normally their x1 is positive value, right? And their x2 is most part is the negative value. So in order to separate these 2 groups, we call the red stars is in group C1. So they have their coordinate, and also we give another feature is their value equal to 1. So if any point or any pixel, any stars, their value equal to 1, that belongs to the red group. And if the value equal to -1, they belongs to the second group, the blue group. So this is our, we know this problem. This is some of the condition we know. So then we have a lot of other extra input stars, like all these black stars. From here, it's easy for us to tell, okay, this black stars belongs to the red group, and this black stars belong to blue group. It's very obvious for us, but not very easy for computer, because computer only know their coordinate x1 and x2. The computer need to figure out for any given new black stars, is that the value equal to 1 or value equal to -1. So that is this computer experiment really want to do. So here we can see, okay, if we can draw a line along this green line, if we can draw a green line and the line, anything above the line, like on the left top part of the line, we know that one belongs to red group, otherwise belongs to blue group. So our goal is to figure out whether we can find such a line. If we can find such a line, we can tell, okay, below or above. So in this 2-dimension plane, we know it's easy to define a line. It can be w1 x1 plus w2 x2 and plus w0 equal to 0. So here is we know if we using x2 on the left side, and then over the w1 over w2 will be their slope, and the minus w0 over w2 is their interception. So that is our goal for this specific problem, is we want to see whether we can find such a line. So that can easily separate these 2 groups into either top or the bottom. Okay, this is our problem we try to solve. So in order to solve this problem, we need to figure out whether we can find such a w1, w2, and w0. So here we construct a 3-input, actually 2-input, 1-output, 1-neural perceptron. Okay, this is the perceptron we constructed. So have 2 input x1 and x2 and have 1 output y. So go back to this slide, we can tell for any input stars, if we know their x1 and x2, that's their coordinate, we can tell that one belongs to 1 or belongs to -1. So and the goal is figure out whether we can find such W1, W2, and W0. So W0 is for another extra input, 1. The 1 is extra input, we call that one as the bias. So the goal is find out whether we can find such W0, W1, and W2, which can separate all these pixels. Then the question here will be, okay, here I already give you, okay, we construct a 2-input, 1-neural perceptron. And the question you will ask is, why here we only need 1 neuron? Why we don't need 2 neurons or more neurons? Or why 1 neuron is enough? So look at it here. We can give a simple example, okay? Let's choose one point from the red group, so this point, and we know their coordinate equal to x1 equal to -2.5, and x2 equal to 7, and we know there belongs to the red group. Therefore, the desired response equal to 1. So this for this pixel, and for another pixel, this pixel is its coordinate x1 equal to 15. And x2 equal to -4. And their property or their feature is d equal to -1. That's their desired response. So if we put them together like it's here, assume we know W0, W1, W2 equal to 26, -19, and 57. Assume we already know this optimal perceptron's weight. Optimal synaptic weight. And now for this input, for the V1, we know their coordinate equal to -2.5, 7, and the desired response equal to 1. So here we use the W1 multiply x1 and W2 multiply with W2 multiply with x2 and plus the bias. That one equal to 472. And then for the next input, this one, x1 equal to 15, x2 equal to -4, and d equal to -1. Let's plug all this here. 15 multiply with -19 and -4, 57 plus 26 equal to -487. So here, you know, in this neuron, what we do is just do the weight summation. So all the input multiply with their weight and then sum together. So given the x1, x2 from the red point and x1, x2 from blue point, we can get the V1 and the V2. That is the output for this neuron. And then here, look at it here, the phi is the activation function. So here we only choose a very simple one. Choose like a threshold. If the v is less than 0, that output equal to 1. If v is larger than 0, the phi v equal to 1. If v less than 0, the phi v equal to -1. You can see just like a threshold, either output equal to 1 or -1. So therefore, look at this one. We have the V1 as we have the x1 is -2.5 and x2 equal to 7. That is this red point. And then what we do is we multiply their weight and plus the W0, we get 472. That is the V output. Now that's the V. and then V as the input to the activation function. So this is the activation function. If the V is larger than 0, the output will equal to 1. So therefore, we know this is the 1. So similar for next input, 15 minus 4. If we multiply them together, you get a minus number. It's minus 487. So this one is the input to the activation function. We get the output equal to minus 1. So here we can see even the coordinate for x1 and x2 could be different value. But because the summation happens at the neuron and the output goes through an activation function, therefore one neuron should be good enough. That means for this problem, for this linear separation problem, one neuron plus one activation function can do this job.